Welcome to thru.
Hello and welcome back to Calculus2, section 6.7, applications of integration. So we're talking about physics. We're going to first take a look at density and mass, and we'll take some problems with work, which will involve force, and so on. So mass, why red? Mass. Mass is defined as density times the volume. And I like to describe mass as a quantification of physical existence. If the object exists in this universe, it must have a mass.
Leave.
Leave? No. So you have the subatomic particle, and sure, yes, if something travels at the speed of light, but light is described as wave and the particle, and I can just consider light to be a wave, so don't worry about extraneous cases. However, you, right, who is a physical entity, you have mass. You also occupy volume, right? Not as much as me, but you do. And you are dense to whatever density you have. So now we can calculate your mass if we take your average density and multiply by your volume. Unit of mass is kilograms in metric system. And does anyone know the unit in imperial system other than Evan? Of course he knows. Anyone? Unit of mass.
Grams.
Grams, that's metric. So grams, kilograms, decagrams. Evan?
Snails.
No, slug. Snails. So yes, it's slug. And yeah, I know. Well, one slug is about 15 kilograms.
You gotta know that.
So what happened?
You have to know that.
No. Ignorance is bliss, right? I know. So now we can define density function we can label it as rho of x, as the book is using. There's some Greek for you right there. Function rho of x is a function which describes density of an object. You know that certain objects are uniformly dense. So if you take a solid piece of metal, that should be uniform density. If you take a solid piece of plastic, again, uniform density. But if you take a piece of wood, well, that's not going to be uniform density, right? So there are certain, also, if you take a look at a human body, depending on where you poke, right, you might hit the bone, you might hit the muscle. So not uniform density for the human body. So we can, depending on how complicated it is, we can figure out maybe the function which describes that density. And we can use it, right, to calculate so we can use that density function to calculate the mass of an object. So if we, so mass of a one-dimensional object, now that means the object is long and very, 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 very thin. It's still a three-dimensional object, but we call it one-dimensional because one dimension is pretty much all that it's important in that case. Like if you take a look at a wire that it's very, very long, you are only practically concerned with the length of that wire, not worrying that it's, you know, that it has actually, it's a three-dimensional and so on. So in 1D, we are going to define our mass. So mass in one dimension is going to be mass equals integral a to b of rho of x dx. And to illustrate that, I'm going to draw a rod from A to B that will have density function rho of x. Now, this rod could be uniform density. If it's uniform density, then rho of x is equal to, I don't know, 7. But if it's a variable density, then we are going to have some kind of a function. So, uniform density example is rho of x equals to 7, and variable density is rho of x equals to 1 minus x squared, or whatever. So we can have either uniform density or variable density. What we do with these is we put these in the integral, and then we compute the integral. So let's see if the book trying to jump to homework and goes page by page. For whatever reason, this online service is working worse every time I use it. All right, there we go. So let's work on two examples here. Say we have problem 12. Want to calculate the mass given the density function of 5, so equals to 5e to the negative 2x on the length 0 to 4. So all we need to do is to feed this into integral, compute integral, and call it a day. Mass equals integral from 0 to 4 of 5e to the negative 2x dx. The integral is negative 5 halves e to the negative 2x computed from 0 to 4. That is equal to negative 5 halves times e to the negative 8 minus 1. And that's equal to some number. What happened? Yes, yes. Then you can go and you can figure out your number. So we have exact value, and that exact value is negative 5 halves e to the negative. You can write this as 1 over e to the 8th, if that makes you happy. Now, we can also use the to find mass. We can also use piecewise functions to describe our variable density. So variable density, let's say it's x squared for the length 0 to 1, and it's x2 minus x if the length is between 1 and 2. Well, in this case, you have to set two separate integrals and add them for the total mass. So we are going to have the integral, so total mass would be the integral from 0 to 1 of x squared dx plus the integral 1 to 2 from x2 minus x dx. So this is x cubed over 3 computed from 0 to 1 plus the integral 1 to 2 of 2x minus x squared dx. The first calculation gives us 1/3 plus the second one is x squared minus x cubed over 3 computed from 1 to 2. So that's 1/3 plus. I have 4 minus 8/3 when I plug in 2. And then minus 1 plus 1/3. Great. 4 minus 1 is 3. And then minus 6/3. So the whole thing is 1. Good.
For this one, it doesn't matter which one is first, because it's addition, right?
Yeah. So that would be calculation, what a mess. More interesting than that would be work. Work is defined as force times the distance, and if you're pushing something straight, right, at uniform speed or whatever, it's going to be very simple arithmetic to calculate. However, it is not entirely true that you just push something with the equal strength all the time. Just like it's not entirely true that you are always driving 40, if your average speed is 45 miles per hour, that you were always driving 45 miles per hour. For a fact, I know that you didn't jump into the car, right, at your starting destination while the car is moving 45, right? So you got into the car while the car was not moving, and then you accelerated to whatever speed, and then you maybe stopped on a stop sign or a red light or whatever, and then also you parked once you reached your destination. You didn't jump out of the car at 45 miles per hour. So for speed, you have that 0, and it goes up, and it goes over, and so on. Same thing if you're trying to push an object. If you want to push anything, right, you don't get to just start pushing at 100 newtons, right? There is this initial contact, and the force gradually increases from 0 to 100. So your graph in time, as you are applying force, F, you start with a 0, it rapidly rises, let's say, to 100 newtons. You're pushing 100 newtons because you're extremely weak, obviously, it's nothing. But you're pushing it with 100 newtons force, and then you're pushing, and then over time you're getting tired, and then you are pushing less, and then you just quit, right? So this would be the graph of what the force actually sees in time. And as you can see, that's not a uniform just force across. It's 100 newtons, right? That's ideal case for easy calculations. But in calculus, we worry about every bit of a change. Just like you are not getting into your car as car is moving 45 miles per hour and jumping out of it at 45 miles per hour to claim that you were always driving 45 miles per hour on average. The same thing happens with the force. So the force is going to be at 0, and then you are going to really add a lot to it. So force is really rapidly going to rise up to, let's say, 100 newtons. You will be pushing. Eventually, you're going to get tired and then quit pushing at whatever time over here, TF, time final, whatever. So now, because we have the variable force, we can use the function that describes the change in force, as we can see. We can plug that into the integral dx. Dx is going to give us distance. So force times dx is actually force times the distance, which will give you work. So the integral for work must be the integral from a to b of the force function, whatever the force function is, times delta x, so dx. This would be calculus formula for work, and you will you would have to use this one because, as I said, you get tired, you get motivated, right, through the push. That's for athletes what happens, right? If they're running and they're really, close to that finishing line, right, they get the adrenaline shot because they want to win, right? They run a little bit faster at the end, right? There's extra push. So that could happen as well, right? So maybe you are pushing a heavy crate and you are a very devoted laborer, so you just, you're very close to the end, you just have the extra push. At the end, the force goes up, right? See, I know you discussed that before the class, so I have to add that in. So now, for the force, it is interesting to take a look at some of these cases. When you lift something, right, you are beating gravity, right? Gravity is the weakest of all forces we have, and it's very easy to beat gravity because you can jump, you can lift objects and so on. Everything of that sort is acted on by gravity, and it's pulling towards the center of mass, which is center of the Earth. And you are beating all of that by lifting any. So technically, every single one of us is stronger than the entire planet, right? Because we are able to beat the force of the planet, right? Because you can lift stuff. So think about it that way, and that's your... I'm not going to give you any more compliments. That's enough for one day. No, actually, you're out for the week. Actually, wait, week is over. That's it for the course. Done. The rest is just going to be doom and gloom. So now, when we are thinking about these things, right, you have an object that you can lift, and you have an object that you cannot lift, right? It depends on the mass of the object, which also depends on your strength, right? Which is the number of newtons that you are putting in to lift objects. Now, I would like to get you thinking about the pile of a chain. You know what the chain is, right? Just think of a chain being on a pile, and you pick up one end of the chain and you start lifting. Is it the same as if you were to pick up the entire chain and lift? No. Right? It's not the same. Because if you have, let's say, 3 feet long chain, and it's thick chain, right? So it will be heavy. If you pick up a little bit of that chain off of the ground, you are going to pick up not the entire chain. You are picking up just some of the chain, right? And then as you are lifting more and more of the chain, right, the more weight is added, so you need to have more force and more strength to lift things. So as you are lifting more and more chain, it becomes harder to lift. Obviously, if you are able to lift the entire chain, right, at once, then you will be able to lift the entire chain off of the ground, lifting little by little. But the interesting thing to consider there is that the weight of the part that you are lifting is increasing as you are lifting. So it's increasing with the height. The same thing happens when you are driving. Your car has certain weight, right, which is the car plus all of the garbage you have inside. And then you also have gas. Now you have certain weight. Sit in a car, so it's car plus the garbage plus the gas plus you. As you are driving, what's happening with the weight of the car? Decreases. Why? Gas, yes. So gas, which was the liquid in your reservoir, is getting converted into heat, right? Most of it, obviously 75% of it is wasted, 25% is used to move you from point A to point B. So you have the weight of the car is going to decrease as you move forward, right? So with distance or with time, the weight of the car decreases because the gas is getting depleted and converted into energy that propels the car forward. So now, as you can see, the force, right, in both of these examples, whether it's the force that moves the car that comes from the gas, or the force from you lifting the chain, is variable, because you don't need as much force to move lighter objects. That should be common sense. So when you are driving your car, and let's say in your trunk, the entire year, for whatever reason, you have all of your camping gear, all of your snorkeling gear, all of the stuff, right, because you just don't want to pack that and put that into your trunk, you know, because you go and do this activity twice a year, let's say. If you drive that stuff in your trunk all the time, well, clearly your car is heavier and it will be using more gas to go from point A to point B because it has to move heavier weight. It's very simple. So the force is variable. Now, as the gas from the trunk, as the gas gets depleted, the car is lighter, so it needs less force to move, right, the car. So variable force inside the integral makes a lot of sense, and you integrate that because force times the distance. We know that the dx has the b minus a over n, right? That's delta x. So a and b are in there, and that is your force times the distance. So now another concept that pretty much all of the books like a lot is the concept of a spring. The spring is going to always oppose the push or a pull that is exerted to the spring. Spring would like to be in equilibrium, like everyone else, right? You want to be in equilibrium at all, right? You don't like anyone poking into you at all times, right? You just want to be left alone. So that's called an equilibrium. So the same thing, the spring, right? Just want to be left alone. Now, what happens when you compress the spring? It pushes out, right? So you use the force, right, to compress the spring, and then the spring is pushing back because it wants to extend the other way. Same thing happens when you stretch the spring. You are stretching the spring with the force outward. The spring force is pushing in. Now the force for the spring. So here let's talk about the spring. Spring is the coil. You should be familiar with the spring. I hope at least once in a lifetime the pen fell apart in your hand, and you were able to see the spring and maybe play with it. The spring has the variable force given by the k times the distance. K is the coefficient spring constant. So k is the spring constant. And this spring constant is related to what type of a spring you have. Your car has the shock absorbers, right? Shocks. Those are springs. A train has one, truck has one, and your pencil that you click has one, right? The difference between these springs is actually that K, right? The higher the number, the more stiff the spring is, it's harder to compress it, right? And you can't just swap, you know, the shock in your car with a little spring from your pen. It's just not going to work. So this spring constant is actually the one that it's telling us how much force per meter we get as we compress the spring. So now it is going to be variable because if you compress the spring a little bit, it is going to push out a little bit. If you compress it a lot, it is going to try and push out a lot. Just the same like a rubber band, right? If you stretch the rubber band a little bit and you let go, it's just going to go a little bit. If you stretch it a lot and let go, it's going to go far, right? That just means a lot of force in the system. So it's a variable force. So now I have that the work integral regarding this is going to be kx delta x, right, for spring. And then we are going to say that A and B are positions where spring, let's call it spring end, spring, where's, I don't know how to, hold on, I have to reboot. So A and B are positions of the end of the spring. Say it that way. The formula I wrote up there is called the Hooke's law, and our textbook is not using negative. Vast majority of the books is using negative because of the notion that spring always opposes whatever is done to it. So if you stretch it, it wants to compress. If you compress it, it wants to stretch. So the formula should have a minus sign right there, but whatever, right?
What does that mean? Negative change the whole answer.
It does, but then in a concept, you have, see, in physics, negative is just showing the direction. So, and you are actually allowed to take any direction as your positive direction, because there is no absolutes in physics. There is no state of absolute motion. You cannot claim that you are standing or sitting still right now. You cannot claim that you are not moving. And the reason is, right, the planet is rotating, right? And then the planet is also going around the sun, right? And the whole solar system is rotating in the galaxy, and galaxy rotates, and then the galaxy is moving, right? So you have to always pick a reference point, right? So now I'm going to say that you are at rest in respect to me, right? But then even if I start moving, right, then again we have to debate and talk and set up some reference points. So in that respect, if I say that gravity should be called negative g because I like the idea of things falling down, right, if it's going down, to have a negative number, some will argue that, well, just why we use gravity all the time, so let's just keep it positive, right? And then whatever is going the other way, which means going up, will have a negative sign. So the same thing goes here. It's a convention. Either way, as long as you understand that the spring always wants to do the opposite thing, and then obviously since it's physics, right, you look at the problem and common sense, and you know which way, right, if you assign plus there, then the opposite motion must be minus.
If you lack common sense.
Don't do physics.
Oh, yeah.
It's the best prescription I can give you. So, at the question, I mean, if you like common sense, there is, there are other things then, right? Yeah, I mean, imagine how sad this world would be if everyone were physicists, right? There would be no color. Look at this classroom. Look at this. Do you think that actually physicists came up with this? No. They can tell you the wavelengths of each of these colors, but it's not going to make it nicer, right? So yeah, we need everyone. So yeah. Anyway, going back to the problem with the spring, how about we compress and stretch the spring and do some of that work. So there is a problem worked out in a textbook. I will pick a different problem from homework so that you have a few different reference points to look at, if this ever loads. How are you? It's gonna take some time. Aha. Compressing and stretching a spring. Problem 20. Suppose a force of 15 newtons is required to stretch and hold a spring of 0.25 meters from the equilibrium position. So it's required to stretch and hold spring 0.25 meters from equilibrium. Find the spring constant K, and then let's see what happens to, push it back to point 2 and so on. So, first off, part A, what is K equal to? Well, force equals Kx, and you know that the force required is 15. K is what you're looking for, and then you went 0.25. From here we'll see that K is equal to 60 newtons over meter. So we have a spring constant of 60 newton meters. Now, what this does is this creates immediately creates a function fx, which is kx by Hooke's law is 60x. So this is our variable function for this spring. It's 60x. And now we can go and look at other questions. How much work is required to compress the spring 0.2 from its equilibrium position, right? To compress the spring 0.2. All right, so how much work is required to compress 0.2 meters? So now we draw a spring. We can attach a body, right? Like a crate or something, whatever. We're going to push on that with a force. We just know that we want to compress from equilibrium point, which is here, and we want to compress it this way to negative 0.2 meters. So wherever is the zero, wherever is the spring, right, when the spring is comfortable, that's the equilibrium point, and then you can compress it or you can stretch it. You're stretching it, you go the other way. We have the force F applied that way. So we are looking for the work done to do this. So what do I have? Well, I have integral from negative 0.2, from 0 to negative 0.2. We'll talk about that. And then we have our force, which is 60x dx. Now, we integrate this and we get 30x squared from 0 to negative 0.2. And then we plug in the values. When I square 0.2, I'll get, well, we can write it, negative 0.2 squared minus 30 times 0. That's gone. This is going to be 0.04, so 12 joules, right? Everyone gets 12? Good. Now, you might be wondering, well, hold on. You said from 0 to negative 0.2. Why? Well, what's first, what's the second, right? Where's the first frame? If you think of it this way, the first frame is here. That's before I did anything. The object sits at 0. And then I pushed it, so the second thing that is happening is the object is now at negative 0.2 location, right? And then those are the limits. We still have, and we are still experiencing positive work because we did work to push the object. So this answer needs to be positive, right? Unless the object is pushing us. If I'm defining, right, me pushing an object to be positive value, then object pushing me is going to be negative value. Yes?
What if it was 60x squared? What would that, if we produced a negative value, what would that mean?
That means you're being pushed, as I said, right?
That means you start at negative 0.02 and you ended up at 0, you did no work, brings it to work free. Yeah, he back there looking like, whoa.
It's the formula, man.
That's all you need. Not for
Concept.
Not for Cal 2.
Oh, good thing you're not going to be engineer, so don't worry about it.
He is an engineer.
Yeah.
No, that statement is not compatible with engineers.
There's a lot of graphing.
Maybe computer scientists at that time.
No. No.
Yeah, I'm a comp though. Yeah, pretty good.
All right, so part C. How much additional work do we need to stretch the spring from 0.25 to 0.3? Right? So just how much additional work? So we are only computing that extra work. Spring is already stretched. We know we used 15 newtons to stretch the spring to 0.25. That was in the problem. Now we want to calculate how much work it takes to stretch that initial 0.05. So we were supposed to start at 0.25 and then stretch it to 0.3. Well, that's just limits. 0.25 here, 0.3 over there, and then we still have our 30x dx, sorry, 60x dx.
On the top, use 0.20.
Yeah, it was different in the text, right? These are not related. From 0 to 5 to 0.3. So now we have 30, and then we have 0.3 squared minus 0.25 squared. Yes?
If they were related, would part B have been like 0.25 and then 0.05? Like the bound. Like, was it pushing back from 0.25 back 0.2?
Yes, you would have to go and start from that, yes.
Right.
So now this is equal to some number, right? You have 30 times 0.09 minus 0.0625. Or something like that. That's 30 times 0.0275. Which is 0.275 times 3. That's what? 600, 210, and 15. Gives us, that's an 8, right?
Yeah.
So 0.825 joules. Or whatever your calculator gives you. It's interesting, interesting stuff. Now, we can calculate work because we can calculate, figure out the force needed to do something. We know the masses and weights and things like that, right? We are calculating work because work is directly connected to power. And since we are not doing physical labor pretty much at all, we have machinery to do the labor for us. Machines are ran by electrical motors, and electrical motors in their specs have power. So the work done is related to power, and if I know how much work needs to be done, I know what type or how powerful the motor needs to be. For instance, motors in cranes and lifts and so on that are lifting heavy stuff, right? I would like to know how much work needs to be done, and then I know pretty much what the power requirements are. Now, obviously, no one lists, work. They say, okay, this particular setup can lift so much in terms of weight, right? Because everything gets converted back. But if you have, let's say, well, hopefully not, if you have water in a basement or something and you need to pump that out, or you want to pump out the water out of the pool at the end of the season, or you are supposed to design the new pump at the gas station forever. So whatever, you are just pumping liquid. Oh, actually you also pump blood, right, into the system. So all of these things will actually have some kind of a motor that is pushing this liquid. And again, the liquid is going to have certain density, it's going to have certain mass, so there will be work done. The work is related to power. So then you go to, let's say, Home Depot, not in your case, you go to Home Depot and you buy a sub pump, right, to pump the water out of the basement, or you buy a pump that will pump the water out of the pool, and so on. And those are rated in horsepowers, or which is unit of power, or watts, right? That's just a simple unit conversion between the two.
How did you say watts?
Watts.
Oh, I heard watts.
Yeah, watts.
Huh?
Yeah, watts. So,
What's going on?
Twilight Zone. So, we would like to take a look at the requirements, right, the work requirements to pump the water outside of the pool or outside of the some body of water, whatever it is. And there is a formula. So, pump liquid. Work is equal to integral A. I don't like A and B, I like C and D, because this is a Y integral. You pump water vertically up, or gas or something, because the gas tanks at the gas stations are underground. Every time you drive on a gas station, you drive over all the tanks that are underground, and you have all of those connections somewhere in a corner where the big truck, right, and they connect everything, and everything goes underground. So you will be pumping the water up, you will pump the gas up, right? You pump. So that's why I like C and D, and all of the functions that are given in terms of Y, because it's vertical distance. So what we have is rho G A of Y D of Y dy. So this is the formula. And I will give you exactly all the aspects, like what is what here. So rho is the density. So what are you pumping? Water or gasoline or blood, right? They have different viscosity. It's going to be different, right, to pump those. We have gravity. That will not be helping us, right? So we are using, whether we are doing metric system or imperial system, we are going to use either 9.81 or 32.2 feet per second per second. This is the area. We'll talk about that as well. And then this is the distance, vertical. Let's call it vertical distance. Now, to see these guys at work, I'm going to refer to the imagery from my childhood. So, where I grew up, there was, well, there still is this huge dam in a town where I grew up. There's this huge dam that they close, and the river fills the huge area where you can swim. It's really deep and it's a lot of fun. Now, to the side, there's a little channel that channels the water away from that place where people have fun, and I don't know, half a mile away, that channel leads to a place where the big trucks go in and they fill the trucks with water, and then they use that to wash the streets. Now, as a kid, I always loved to go and actually see those trucks being filled with water, because I was so much power in just channeling that water. Now, the pump, right, was all underground. It was coming out of that channel. It was this big nozzle, right, that went like that, and then you park the truck underneath, and it just dumps all the water inside. It filled trucks very, very quickly. It was a lot of water going out there. So now what I'm going to do is I'm going to recycle that idea, and I'm just going to say, okay, here is the ground. I'm going to connect this to the formula up there, and here is the reservoir on the bottom, right, and the water is getting sucked out of that reservoir. Now, I don't care whether that's a river or a reservoir, but we are going to use the reservoir because we will be emptying pools and whatever else. So now, if you are looking at this, the water is getting pumped from the bottom of the tank. You should have this concept in your head because you drink liquids using a straw, right? If you're using a straw and you just put the straw just to the top, right, of the liquid, you're not going to achieve anything, right? You actually put the straw all the way to the bottom, and then when you drink, right, the liquid goes in from the bottom. Your gas tank has the same concept, and everything else pretty much that we have has the same concept. So you are draining stuff on the bottom of the tank, and then bringing the stuff up. Now, when you are draining from the bottom, note that the level of the fluid and the level of the fluid inside the tube is the same, right? So there is no work that it's needed to go in there. So all you need to calculate is how much extra work you need to get that to the level of where you pump. So that distance is given as the distance dy. So this distance here is given as the distance dy. The shape of the tank is going to be your AY, which is the area of the tank, right? So that's going to be given in the geometry. And now you have the right rho is going to be the density of what type of liquid you are pumping, and then G is the gravity. So all of these concepts work together, and you get to pump out the liquid out of the reservoir, whether it's gas or water or whatever it is. Let's take a look at an example of this that will help us. One of the project questions that circulates in that pool of questions is actually a question that has to do with you drinking from some kind of a container, say a soda can, right, with a straw. And we can figure out how much work, each time you take a sip, how much work is actually done. And then you can also translate that, really funny stuff that you can do. You can transfer that into how many calories you actually used up to take a sip, right? How much energy did you burn? Because the amount of work that you have done to take a sip through the straw, which is actually this concept, is so the amount of work done is the amount of energy that you can convert into. All right, so that would be a good conversation starter. You know, you're outside and you go, so do you know how much energy you have just used to take the sip out of there, right? And from there, obviously, the person will never talk to you, which is a plus. You can play video games in peace. So the problem would be where you take the soda can or whatever. So we have a soda can here, and we have a straw. So there's the opening in the soda can, and then we have a straw that it's inside, and that straw is supposed to get the liquid out. Again, whatever it is. Could be water, could be Sprite, could be blood, whatever is in the can. Vampires? Exactly. So now the can is full of liquid to certain level. So let's say that the can is on the ground level, right there. So as soon as I say ground level, then that's where the 0 is. Say that the can is 10 units tall, and that the liquid is at the 7 units of height. So that's what we have. We have a 0, and we have 10, and we have 7. And let's say that the straw is additional 3. So that's the straw, the tip of the straw is 13 above the can. So you have the ground level, that's where the 0 is. I just noticed that these are not the same height, so here. That's the ground, that's where the 0 is. So you have the ground where the 0 is, the liquid is up to 7 units. Liquid is up to 7 units, and then you have the can is up to 10, and then the straw ends at 13. The radius of the can is what? What should I put here? 4? Okay, fine. By popular demand, 4. What happened? Exactly. So now I have all of the measurements. Guys, these measurements are something that you can actually do, right? All of these measurements are accessible to you. If this is a problem on a project with measuring with a ruler, right? You get to measure the height of the can, the height of the liquid, the length of the straw, all of these units, and the diameter, which gives you the radius. So all of the units and dimensions that I put on this thing, you can actually measure with a straight edge and a little bit of OCD, which is necessary to be a successful pretty much in anything. And you can do all of these things on your own. So now we have this concept. So now what I'm going to do is I'm going to set up the integral that calculates the work that needs to be done for this liquid, for all of this liquid. So let's say this is going to be one long sip that will just drain all of this liquid out, right? So work done in this case is going to be the integral from A to B. All right, so what am I draining? I need to drain the liquid from 0 to 7. So the limits of the integral are 0 and 7 because I am draining that much of a liquid. If the can is full, then it's 0 to 10. So whatever I have inside is what goes into the limits. Now, rho, I'm going to leave that as a rho. I can put 1,000 if it's water, but then, you know, maybe it's Sprite, maybe it's something else. So whatever it is, right, rho will describe what type of liquid you have in a can. Each one of the liquids has its unique rho. And then we also have G. I'm going to leave it as G. Sure, we can put 9.8, but yeah, right. The next part is to talk about the area. So this is cylinder. So the cross-sectional area here is going to be a circle, right? And the circle, so I'll just put the arrow right there, say circle, whose area is pi r squared, and pi r squared is, in this case, always going to be 16 pi. We have constant surface area in this case. So my A of y is constant. It doesn't depend on the shape. Now, if you take conical shape, if you take, maybe you have a spherical mug or something, well, then your surface area changes with the height y, and you need to be able to express that change. So that's going to be next problem, but you need to be able to express that change in terms of y. Well, in our case, we just have 16 pi, so we'll plug that in there. And now we are at the distance that needs to be, so this is the distance part right here. And then you have dy. Now the distance part is, if you think about it a little bit, the liquid just needs to clear whatever is above the liquid, because whatever height liquid has, you get that much height of the liquid in a straw for free. All right? So the work is only done to get the liquid past the height of the liquid. So the height that it needs to reach is 13, and you subtract y, because from 0 to here is y, right? The y could be at 7, could be at 5, could be at 3, could be at any point between 0 and 7. So any value at which liquid could be is described by y variable, because it's going to change, right? If it's changing, we use a variable, and that's between 0 and 7. But you need to go all the way. So this is the red part over here is what I need, right? So you take everything, which is 13, and you subtract what you get for free, because you put the straw, the level is the same, and then you just have the distance 13 minus y. That's the only distance that actually where the work happens. The rest is free.
Isn't y given? 7?
Yeah, but as soon as you start taking a sip, that 7 goes down, which is the reason why I said, right, as you drive, the gas gets depleted. So the mass of the entire car is lighter. As you're lifting the chain, you're adding more chain, so it becomes heavier, so you need more force. Right. So the same thing here. As soon as you start drinking, the level of fluid is going to start going down. So that's, yes, so that's why it's Y. I can't call it 7. Because in the next instant, it's going to be 6.7. And then it's going to be 6.3. And it's, right? Depending on how, what the SIP is. Now, if this is a problem on your project, you will actually have to Google what is the average SIP, right? And believe it or not, it's actually a number that is average. Yeah, exactly. So you would actually have to Google average SIP, and then you will have to go and figure out the rest of the stuff. The project directions are almost non-existent. You just say, figure this out, right? And then you go and you figure it out. It's not like a problem on a homework that it says. This is actually more like the problems that you would face when you start working, right? You sit in a meeting, there is a meeting, and say, okay, Joe, that's it. Go figure it out, right? And you either go figure it out or you're fired. Right? That's what it is. There's no spoon feeding, and no one is ever going to ask you to solve an integral, because $300 computer who is going to do that much faster than any of us. So, you know, no integration, no derivatives, none of that stuff. You sit in a meeting, it's all words, which means words problems, right? And then you have a diagram, and then as an engineer, you go and you figure it out. That's that. All I need to do now is to integrate this. So rho is a constant because the liquid is not going to magically change. Gravity is a constant. 16 pi is a constant. So all of that stuff gets kicked out in front of the integral. So 16 pi rho g goes in front. And all I have to integrate is 13 minus y. That becomes 13y minus y squared over 2. Computed from 0 to 7, and all of this is going to be some number times rho g. Now, again, as I said, if you have the water inside this can, you put 1000 for rho, and you put 9.8 for g, and then you get decimal number that you are looking for. Yes?
This is like a soda can. I know you give the example of a ball, how like the surface area like it kind of grows as it would go down.
Yes.
But it'd be like the same formula, it's like the same shape. What if like with a like a Coke can, how it like goes out and goes back in again?
This Gatorade bottle has it, right?
Yeah.
It goes in.
So, yeah, there's something like that.
Well, that's, yeah, you have to capture that in that AY piece. AY piece is the one that deals with those kind of kinks, right, that go in and out. So the next example that we have is going to be a cone, and we are going to drain the cone now. Now the cone is going to have the changing area, so you will see that part in this next example. So let's talk about the spicier case.
So we would never have to like really worry about trying to do a gear about like all the changing areas?
No, because education is terrible. That's the best answer I can give you. And if you don't like that answer, then that's your problem.
No, I don't have to do it on
So here I have a conical reservoir. Why would you want to have a conical reservoir? It's very easy to put it into the ground. Just bang on the top, right, and it just goes in, right? And you just fill the hole. You're done. No? All right. We have the conical reservoir just because we can. That's the basic premise of it. I'm going to have, again, a nozzle, right? So it's draining, right? So this cone, let's again set it to be 10. There is 0. let's put this at 15 now. So you can put feet if you want. Let's use the same radius because we can. 4 feet radius on top, and then 10 feet. And yeah, let's put liquid at 7 again. Who cares? So we have the liquid over here, and the liquid is at 7. Technically, this is one of the most important sections of the entire Calculus 2 if you are mechanical engineer, let's say, right? Because this is the stuff you're working with. So now you have your y-axis set up. You have the 0 level, the liquid again at 7, the height is 10. New height for the nozzle now it's 15. And we are supposed to set up. Now again, as I said earlier, because the liquid is at 7, over here at 7, I'm getting that much liquid for free. All right, that's it. So this level is going to be the same. So I have that. So all I need to do is to figure out this much of a distance here. And that distance in terms of y is going to be, as we saw, 15 minus y. So that's the easy part. And we can also immediately set up the rest of the integral. We are draining the entire cone, so we want to drain everything from 0 to 7. Maybe you just want to drain top 2 feet. Then it's 5 to 7. Are we clear on that? So if I want to drain everything and the whole thing is full, it's 0 to 10. If there's only 7 feet of liquid inside and I want to drain everything, it's 0 to 7. If it's only up to 7 full and I want to drain top 2 feet, then it's 5 to 7. So the limits are telling us how much we are draining, everything or a part. And please don't ever drain from 0 to 2 because it doesn't work that way, all right? It's going to be wrong answer. So you can only drain the top part. The liquid just moves throughout. So that's that. We have our rho g. Our area goes here. I already know this is 15 minus y dy, so we're good. The only issue that I have here is the issue of the area, because the area in the cone is going to depend on the height of the liquid in the cone. And as you can see, as the height of the amount of liquid is changing, the cross-sectional area is changing. So the more you're draining, the less and less area you have. So now I need to figure out this area here. Now the area of the circle is given by radius squared times pi. Now radius, in this case, this particular radius is not constant. It's changing with height. So this radius is actually radius that depends on y. As soon as I figure out how to incorporate that in there, the formula gets that area piece and we're done. Now, from the blue cone of water, or whatever the liquid is, I can see that I can draw a right triangle here that has the height, which is y, and radius r. Okay? So I have that. And then on top of that, I have the actual full cone that has the radius of 4 and the height of 10. So I can write mathematical proportion from similar triangles that are given here, because these triangles have parallel sides on 4 and R have a common side, which is the height, common angle theta on the bottom. So these are similar triangles. So I can write what 10 is to 4, height is to radius. It's a proportion. You can write these proportions in other ways as well, but this is one of the ways. So now you can see that radius, right? When you solve for radius, it becomes, so radius goes up, and then you have your age is equal to y, right? That's our height. So radius goes, this is y stays, so 4y over 10, which is actually 2y over 5. So radius in terms of y is 2y over 5. So now, since area is radius squared pi, that's going to be 4y squared over 25 pi. And now that gets fed over here, and we have our 4y squared over 25 pi. So I'll go through the argument one more time. Our formula requires the height of the liquid, which was easy, 15 minus y, we discussed that already twice, and requires the area. Since the area is now changing as you are draining, this area is getting smaller and smaller and smaller and smaller and smaller. I need to figure out how to write that area in terms of this changing height. So I get similar triangles going. R represents the liquid, Y represents the height, and then we have 10 and a 4, which are our specs of the container. So now we set up the similar triangle proportion, solve that for R, and then plug that R into the R for the area. And we have, as you can see, A area as a function of y, because you have y squared, right? It's a function of y. Plug that into the integral up there. And now we have to solve. So what's the constant? 4 over 20, so 4 pi over 25 rho g integral 0 to 7 of y squared times 15 minus y dy. You see that the integral is a joke, right? You multiply y squared and you integrate. So the hardest part of these problems is to figure out the area equation and express that equation in terms of y, which is the height. You know that the water will go down as you drain more and more. So if it's not a cylinder, like the soda can or that Gatorade, can you model that for us, please, the Gatorade thing? High up, yeah. You see, that's a cylinder. It has uniform, so now your bottle over there seems that it's curved inside, right? It's curved. That cup, Ravi, the white one, yeah, all the way, that cup is also has curved edges, so both of those have varying surface area as the liquid is getting drained. The soda can here, the blue one, and the green bottle over there are both cylindrical, so they fall into the easier case where the radius is constant, therefore area is constant, so we don't have to worry about figuring out area equation too much. All right, so let me just quickly run through this. This is 15 integral of 15y squared minus y cubed dy from 0 to 7 4 pi over 25 rho g, and now I have y cubed over 3, so that's 5y cubed minus y to the 4 over 4 from 0 to 7. We don't have to worry about 0, right? So I have 4 pi over 25 rho g, and then I just have 5 times 7 cubed minus 1/4 7 to the 4th, and that's equal to some number. Times rho g. And here is the go and figure out the decimal if you love it so much. Bueno? Time for a break.